Hi everybody, I'm going to do a tutorial on a really cool application of the law of universal gravitation as applies to orbits. Specifically, the orbits of our planets, or the planets of our solar system around the sun. And I'm going to teach you, as the heading of the tutorial says, Kepler's laws. So these laws, three laws, were discovered back in the late 1500s by an astronomer from Germany called Johannes Kepler. Kepler, you might have learned that name in earth science. And Kepler did some remarkable work. He spent decades looking at positions of stars, especially the planets that were known at the time, charted their positions, and he found some very interesting patterns. Ultimately, since his time was before Newton, he had no physical reason or idea what was going on behind this, and it took a guy named Isaac Newton to take Kepler's laws, which had been known about a century by the time Newton did his work, and figured out the physical basis for it. And so, in the big picture, this is nothing more than the universal law of gravity applied to circular motion. Even though it's not quite a circle, it's close enough. So the derivations I'm going to do on the next page, you are expected to be able to replicate them, because it's really ultimately nothing more than supply equals demand. And so if you understood that from the previous chapter, it's the same idea, except that we have a different equation for gravity, one that's more universal than the mg that we've been using, because we're not confined to the Earth any longer. So let's talk about those three laws. The first two are pretty straightforward. Our main focus is going to be on the third law, because that's the nice application to circular motion. So perhaps the most startling discovery of Kepler's laws, it may sound the most boring or the least interesting, and that he found that the orbits of all the planets are elliptical. And the reason this was so startling, because for about 2,000 years, especially coming from the Greeks, it was assumed that all orbits in the heavens were perfect, and a perfect orbit would be a circle. That was just fundamentally assumed. No one ever questioned it. Kepler worked out that it had to be elliptical to explain certain irregularities in orbits, especially Mars. I'm not going to go into the details of that, but when he had the insight, if I treat the data to fit on an ellipse, everything fell together. That was huge. No one could explain why they're elliptical. It was startling enough that they weren't a perfect circle. But like I said, it took about a century for physicists to figure out the basis for that. The second, and so because it's elliptical, that means sometimes if this diagram here represents the orbit of a planet around a star, and you can see the star in the middle, an ellipse means we're sometimes closer to the sun than we are at other times of the year. In fact, this time of the year, which we're close to the middle of winter, we are actually closest to the sun. And then in the summer, we are furthest. Now, the difference in distance between these semi-major and axis and minor axis, whatever they're called, is actually not very different. There's a small difference here, even though it's exaggerated in this diagram. And so the reason we feel cold in the winter is not because we're further away from the sun, which many people think. It has to do with the tilt of our axis. Right, the second law is a little bit more esoteric. Again, I'm not going to test you on that, but I might as well point it out to you. It basically said planets sweep out equal areas in equal time. So let me try to explain that and tell you what the implications of that are that I do want you to know. So if I take a planet right here and I just let it go through an orbit for a certain amount of time, it will sweep out an area as shown by this. Okay, and you can calculate that area if you understand how to calculate areas of, I don't know what those are called, sectors maybe. And then if I take the same planet at some other time of the year, it will go this far in the same amount of time. So this is a time t, this is a time t. And so the reason it doesn't go as far along the arc, it simply means it's because it's moving slower. So that's one of the consequences of moving in an ellipse, is the planet's speed changes with time. Okay? And so if I make a wedge or a sector going to the sun as one of the pivot points, this area is the same as that area. And if I do it for another time period that's equal to what I designated here, let's say a month, I will get the same thing right there. Okay, so that's interesting. No one could explain why that was, but we knew there had to be some reason behind that. And then really, the most important of his laws was based on measurements of the actual orbits. So I have a chart here of the known planets at the time of Kepler, Mercury through Saturn. And I've also included Earth. And there's two very simple measurements you can make about a planetary orbit. In fact, we talked about this the first or second day of the year. One is the distance to the star you're orbiting, in this case the sun. So we're going to call that R, and note that everything is times 10 to the 9th meters. So Mercury is 49 times 10 to the 9th meters, and Saturn is a whopping 1,300 times 9 meters. There's other units you could use, but this is the most convenient. The second measurement that you can look at is period, simply how much time it takes to go around. And again, everything is times 10 to the 7th seconds. We're not going to use years here because things don't work out the way we want to for the metric system. So the Earth's period, which we know is 1 year, is really 3 times 10 to the 7th seconds. Venus and Mercury being closer have a shorter period. And the further planets have a longer period. So if you plot the period of a planet right here, and you look at its distance, and note that, again, I've built into it these powers of 10, you see that there's a pattern. They're not random. And in fact, if I draw a best fit, it's not a line, I didn't do a great job, but it's a curve. And so we want to understand what is the exact nature of that. So because it's a curve like that, that suggests what is called a power function. Okay? In other words, what we can say is that if we take t to some power, we don't know what, we'll call it m, and it's got to equal some constant k times r to another power. Could be the same power, could be different. In other words, if I write the equation, which we've used before, y equals 1/2 at squared, that's a power function. In other words, y is to the first power, t is our variable to the second power, and 1/2 a are constants here. In other words, if I were to plot y versus t squared and get a straight line, the slope of that would be 1/2 a. Okay, so that's generically called a power function. The trick is, what is the value of m and n? Now, if you look at this curve, it looks like it's a squared curve, a quadratic. It turns out it's not. And there is a method to figure out what it is using logarithms. I'm not going to go into it here. That's something we'll worry about at another time. Okay, but what we found out if you do the analysis, if you take the period and you square it, and you take the orbital distance and you cube it, you get a straight line. Okay, and the slope of that straight line is some number. We'll call it k. I'm not really worried about what that value is, but this gives rise to Kepler's third law of motion. He basically said if you take the ratio, and I'm going to flip things around here on my axes just because it'll make things easier down the road. If I take the ratio of a planet's distance and cube it, and I divide it by the square of its period, it is the same constant value for every planet that we're going to call k. Okay? And that's pretty remarkable. That tells you there's a reason behind that. So if I take 49, if I go to Mercury here, and I take 49 times 10 to the 9th, and I cube it, and divide it by 0.70 times 10 to the 7th, and square it, I will get the same ratio if I do the same thing for the Earth's orbit. So what's going on here? Okay. So like I said, Kepler tried to work this out from a mathematical and mystical standpoint. It took a century before someone more rational took approach to that, and it was Newton. So this proof, notice I put 5 stars next to it, I expect you to be able to replicate. And again, it's nothing more than Newton applied the second law of motion and his universal gravitation to a circular orbit. He just treated the planet as a circle. Even though it's technically not, it's close enough for our purpose. So imagine we have a planet going around a star where it's a distance r away and it takes a period t. He's saying, okay, let's be rational about this. Why does it go in an orbit? Why does it move in a circle? There's got to be some force that is holding it to the sun. What is that force? The only force that makes sense is F of g. And what is F of g causing? It's causing it to accelerate. So we have a supply and demand. So this proof is just built on that. So in the most general sense, we have F of g equals mv squared over r. Okay? So I'm just going to tweak each of those sides in the space below. But that's the start of your proof. The supply force gravity must equal the equivalent of the demand on it, which is the mass of the planet multiplied by the speed of the planet multiplied or divided by r. Okay, so we're going to do 2 side equations before we put together. First of all, how do you calculate the force of gravity? You can't use m of the planet times little g, because we don't know little g. The little g is the acceleration due to gravity on the sun. So we got to use the more universal equation, which we've been using this chapter, which is g, the mass, in this case of the sun, times the mass of the planet, divided by their distance squared. So I'm going to use capital R in these problems. I'm sorry, I shouldn't have written cubed, should be squared, instead of little r. But hopefully that doesn't throw us off. Okay, the second thing is I want to change this mv squared r into an equation based on period. And I mentioned last chapter, this is a derivation you have to be able to do. Okay, so what this becomes is, we know that velocity around a planet is 2 pi r all over period. And there's the period that we want. So I'm going to substitute this into here. And I'm going to come up with an equation. And I'm going to set this equal to, okay, m is still going to be there. In this case, the m is the mass of the planet, because it's the thing that's orbiting. Equals v squared over r, if I plug in this, is 4 pi squared r all over t squared. Okay? Make sure you can replicate that on your own. That's so, so important. So I'm going to just add parentheses around that, because that's just the acceleration part, right? F equals m times a within these parentheses. And now I want you to be able to show that if I take this whole thing, square it, and divide by r, right, like make that capital R, I get what I just put there. Okay, our derivation's almost done. This little parentheses here is the hardest part in my mind, but we've already learned how to do that. So if I cross multiply these two equations, I get, and notice A, that the mass of the planet cancels out when I do that now. Okay, so if I do g mass of the sun times t squared equals 4 pi squared. Now r squared comes over here, multiplied by r gives me r cubed. And then if I move the t to the right side and the 4 pi squared the other side, I get r cubed over t squared. There's Kepler's relationship, equals g times the mass of the sun all over 4 pi squared. Bam. That's a remarkable derivation, okay, for a number of reasons. A, we see that here is that ratio of r cubed to t squared that we saw on the graph. We said it was equal to a constant. In other words, the same value for all the planets. Well, let's look on the right side and see why that is. Well, big G is the universal gravitational constant, so that's the same for all situations. That's the 6.67 times 10 to the -11th. M, the sun isn't changing. The mass of the planets are changing in orbit. The mass of the sun isn't, and 4 pi squared are the same. So the K that Kepler found is nothing more than what I've just circled in green. He didn't know it at the time, but Newton was able to show that's what it is. Now here's what's even cooler about this, is you can take the R value and T value for any planet, plug it into this, and you can solve for the mass of the sun. And so I talked about that the first week of school. This is how you do it. So that's what I want you to do right now. I want you to take Earth data from the chart on the front, and I want you to choose another planet. Write that planet in here, Saturn, Mercury, whatever. It's your choice. And I want you to apply this equation to solve for the mass of the sun and see if you get the same value. Okay? Really important you do that, because you need practice working with these large numbers. Just remember, when you put in R and T, you don't forget the times 10 to the 9th and the times 10 to the 7th. Otherwise, you will not get the right exponent. To check to see if you're doing things correctly, you should get some number, right? The mass of the sun is around 2, it might be 3 or 4, times 10 to the 30th kilograms. So that's the way you'll know if you're doing this right. So keep trying until you get it. It's really important, and I expect you to be able to replicate this derivation. Now, before I finish, and I'll do number 2 in a later tutorial, what if I want to find the mass of the Earth? What information would I need? Okay, and this throws students off all the time. I would still use this same relationship up here, because that applies for any orbiting thing, but I can't use the mass of any of the planets on that chart above, especially the Earth's, because we need something orbiting the Earth. So in other words, if I want to find the mass of the sun, which you did in part 1, or 1 here, you need something orbiting the sun. So if you want to do it for the Earth, you need something orbiting the Earth. So it would make sense we need orbital period t and distance r of the moon. And that's how we figured out the moon, or we could do a satellite that we put in orbit. Okay, I'll do the other two derivations in the next tutorial.